Now in this video we will see the third and last part related to general shape deformation, and we will present in this part surface-based deformation with a focus on Laplacian deformation and as rigid as possible deformation. So first, what is a surface-based deformation compared to a spatial deformation? Let us consider a shape defined by its position pi. We saw so far spatial or volume-based deformation. These were deformation defined in the whole space, or at least in a volume, with a function that associates to any position p a new one q. The interesting point of spatial deformation is that they can be applied to any type of shape. It can be point sets, surface, volume, and so on. However, they are functions defined in the whole space and can be sometimes complex to define. So the control of the deformed shape is also indirect, as we deform the space itself, and then this deformed space implies the deformation of the shape, which is embedded in this space. Also, as the deformation is defined in space, nearby elements are expected to move together, and this can be a limitation in some cases where elements close in space should have different motions. On the opposite, surface-based deformation are deformations that are only defined on the surface and not in the entire space. An example of simple surface deformation is the normal deformation, where q of I is equals to p of I plus the normal ni, where ni is the surface normal at position pi. In this case, the normal of the surface can only be defined at a position pi. It cannot be generalized to an arbitrary point. And we can also have vertices at the same position but with different normals and therefore associated to a different deformation. The good side on surface deformation is that it can integrate or preserve surface properties based on, for instance, on neighborhoods, curvatures, and so on. The downside of surface deformation is that they are depending on the surface. They depend on its representation, on its connectivity, for instance, and so on. So ideally, we would like our deformer to be as independent as possible of the surface parametrization, but only depends on its shape. One of the most well-known surface-based deformation that allows interactive editing is the Laplacian deformation or differential coordinate editing. So the idea is the following. At the initialization step, we encode the vertex positions as differential coordinates with respect to the neighbors. These differential coordinates have the objective to encode how a vertex is related to its neighbors, and they somehow encode the local appearance of the surface. One possible differential coordinate is the so-called Laplacian coordinate that I write delta p. During the deformation, a subset of vertices are constrained with respect to their coordinates, while the other vertices are optimized to try to preserve as best their differential coordinates to keep their local appearance. We can see an example in the bottom, where the red line are fixed vertices and the yellow mark indicates some vertices constrained to be displaced. The rest of the head is deformed such that the constraints are satisfied while preserving the local coordinates. Let us now describe what are the Laplacian coordinates. So for a scalar function f defined in R2 with parameter u and v, we can define the Laplacian as the sum of the squared of the partial derivative or the divergence of the gradient of f. We can also extend this notion of Laplacian to a manifold, and in our case on a surface embedded in 3D space. Laplacian applied on manifold is called Laplace-Beltrami operator. The differential coordinate delta are the value of the Laplace-Beltrami operator applied on the coordinate function f is equals to xyz itself. And it's the Laplacian on the surface of its own coordinates. Actually, a common approximation in the discrete case on a triangulation of the Laplacian coordinates can be very simple. If we call ni the vertices that are directly around the point pi, we call that the RAN ring. then delta I of pi is equals to 1 over the number of neighbors times the sum over j of pi minus pj, where j belongs to the neighbors, belongs to the one ring of the vertex I. Or, in other words, pi minus 1 over the number of neighbors times the sum of j of the pj. So in other words, it's the vector of difference between the point pi and the bicenter of the one ring around pi. Note that this intuition for differential coordinate can be expressed in the continuous case. We consider pi and gamma as a small closed curve around pi on the surface. Then the Laplace coordinate is actually the limit when the length of gamma tends to 0 of 1 over the length of gamma times the integral over gamma of pi minus p dl of p, where p belongs to gamma. And this actually relates to the mean curvature of the surface at position pi and is equals to h of pi times ni, with h being the mean curvature and ni is the normal vector at point pi. So finally, in other words, the Laplace coordinate in the discrete case encodes an approximation of the mean curvature of the surface, which is a local property of the appearance of the shape. Actually, there is several possible approximations of the Laplacian for the discrete case of a mesh. We saw the simplest one, only depending on the number of neighbors of the one ring. It's called the graph Laplacian. And its main disadvantage is that it depends highly on the connectivity and works when you have a regular and homogeneous sampling around pi. If you have some local changes of sampling density on the surface, then the value will change. So it's not a very good approximation of the mean curvature in all cases. There exist other possibilities, all under the form of some linear weights applied to the sum of the vector pi minus pj. A more accurate representation are the cotangent weights, also called the mesh Laplacian. In this case, we have delta I given as 1 divided by the area of the Voronoi cell around pi times the sum over j of 0.5 times the cotangent of alpha ij plus the cotangent of beta ij times pi minus pj. So I don't go into the details of the derivation of this formula that you may have seen in other classes, but such formulation takes more into account the geometrical properties of the triangulated mesh. Therefore, it's more independent of the connectivity. And one of the drawbacks of the cotangent weights is that the weights can become negative in some situations, typically when we have small angles or concave one rings. Note that we can also use the mean value coordinates we saw previously for cages that are less accurate but remain positive on their side. Actually, in 2007, researchers have shown that there is no perfect discrete approximation of the Laplacian operator that would work in all situations. So depending on the structure of the mesh, one may be more appropriate than the others. Let us now derive the formulation of the Laplacian deformation. So we have as inputs a set of n initial position pi and a set of nc soft constraints of position that I call ci. Our objective is to find a new position qi such that delta of qi is equals to delta of pi, and so we would preserve the differential coordinate of the surface. And we would like also the constraints that qi is equals to ci for the positional constraints. So we formulate the optimal solution using a quadratic energy expressed with respect to the unknown qi, and this energy is given by the sum over all the vertices of the differences between the Laplacian coordinate squared, plus some weight on how strong the position constraint should be preserved, times the sum of all the qi minus ci and taken in square norm. Of course, we could insert the omega weights in the sum and set it to depend on the vertex I if you want some constraint to be more or less preserved than others. And actually, the advantage of the Laplacian coordinates is that they are expressed linearly with respect to the unknown qi, as their weights don't depend on qi. Here I'm expanding the formula using the simple graph Laplacian weights, but we could use also the cotangent weights if we prefer. And this energy is quadratic with respect to the unknown qi, so we can solve it efficiently using a least square solution. So for the least square formulation, we reformulate the energy in a matrix formulation with a large matrix M applied to the unknown vector q, and the constant part is in the vector b. Then we know that finding q minimizing the energy is similar to solve the least square problem associated to the set of linear equations expressed in the matrix form. If we look at the reorganization in matrix form, we have q given by all the values of qi concatenated together. M is a large sparse matrix with two parts, the Laplacian part that I call D and the constraint part that I call C. D is square, it's a n times n matrix, and it has 1 in the diagonal and minus 1 over the number of neighbors in the entry ij, when a and j is actually an edge of the one ring of pi. And the constraint part is a rectangular nc times n matrix, where the entry c chi a is the weight omega for I being the vertex index and k is the number of the constraint. And b is a tall vector, where the first part is the differential coordinate of the initial mesh, and the last part is omega times the coordinate of the constraint vertices. So here is an example of triangulation with 5 vertices and 2 soft constraints on vertex 1 and 4, where we would like Q1 to be at position C1 and Q4 at position C4. So the question is, fill now the value of this matrix using the graph Laplacian weights, and we will correct that during the interactive session. So now here is some reminder on how we can solve this least square problem. So we need to minimize the value, the square norm of the matrix M times Q minus B. So the least square formalization says that finding Q minimizing this expression is similar to solve the linear system M transpose times M Q plus M transpose B. This is called the normal equations. So M is a sparse matrix and M transpose M is also sparse and is diagonally dominant. We can use some standard sparse system solver like conjugate gradient or Jacobi or Gauss-Seidel methods. As a reminder, never try to explicitly compute the inverse matrix M transpose M inverse. Only solve directly the linear system. Actually, the inverse matrix would be a huge non-sparse matrix. Also, we can use special solvers dedicated to least square problem, which don't even ask you to compute explicitly the normal equations. Another note is that Qi and Pi are actually vectors with 3 components, x, y, and z. But we don't need to have a matrix with all the components included. Actually, we can solve separately in x, y, and z coordinates. So we can solve 3 scalar problems instead of a larger vector one. Finally, we can note that if we change the constraint position Ci, this is typically the case when we drag interactively some part of the mesh, it only impacts the right-hand side of the equation, which is b. It means that m can be factorized once and reused during interactive deformation. So it's a good point, as the more costly operation is usually to build and factorize the matrix M. However, if we add or remove soft constraints, then the matrix M changes and we need to rebuild and refactorize it. With respect to implementation, Eigen is a nice library that we can use to solve numerically system of equation in C++. It proposes iterative and direct solvers. And if you haven't used it yet, here is an example of solving a dense least square problem. The principle is always the same. First, you build your matrix, you resize it, you fill it with the values. And then we apply a factorization to this matrix to speed up the resolution of the system. Eigen proposed several solvers associated to specific factorization that can be more or less appropriate depending on the structure of your matrix. You can look at the documentation of Eigen to see the different solvers. And then the right-hand side vector can be built and we can call to solve the linear system with the method solve with the right-hand side as parameter. In our case, we have a large space matrix, so we should avoid storing all the zeros. And Eigen proposed dedicated container and algorithm for sparse linear system. So the principle is similar, except that we use the sparse matrix structure. We also fill the matrix with the non-zero coefficient only, and we can indicate in advance to Eigen how many non-zero coefficients we should reserve on each row to be more efficient. Then we can call the least square conjugate gradient solver to prepare a solution using the conjugate gradient approach for this least square problem. Finally, we can build the right-hand side and call the numerical solver on the linear system similarly to the dense case. Note that we can also provide an initial guess to the solver. It can be actually very useful to speed up the numerical solution in the case of interactive manipulation, where the previous solution is actually reused as an initial guess for the new one. And here is some results that you can expect to obtain if you implement it in the lab class exercise. And here we start from a plane and we add some soft constraints that we drag interactively. Note that in the continuous case, it's similar as solving the Poisson equation with Dirichlet boundary condition, although only approximated in our case. And if we start from an initial plane, the objective Laplacian value is 0. So we are actually solving the Laplace equation, Laplacian of f is equals to 0. So the solution, they are already known to be membrane surfaces, which are surfaces with minimal mean curvatures interpolating the constraints. Here's some more results from the original publication of the Laplacian deformation in 2004. Laplacian deformation has been widely developed in research. For instance, it can be used to transfer details between shapes. The details of one shape are encoded in the differential representation, and we deform the other shape to minimize its global deformation while trying to match the differential coordinates, changing the local appearance. Note that these tools are widely known in the research community, but they are not always known and developed in the commercial tools yet. Also, Laplacian modification has been associated to sketch-based interface, for instance, to provide an easy way to modify a shape in sketching its silhouettes. And here the silhouette acts as a soft constraint, and the rest of the mesh is smoothly deformed using the Laplacian method. So far, the Laplacian deformation applies a smooth deformation on the surface. But it doesn't take into account the surface orientation, or more precisely, it's not a coordinate system which is rotation invariant. So the result deformation actually tries to force a specific orientation on the mesh, which corresponds to the original one. And so we cannot model correctly mesh rotation from this approach. So in some case, we would like to see the surface automatically adapt its orientation so that we can handle correctly rotation effects. One extension allowing such effect is called the as rigid as possible deformation that tries to match the differential coordinates but in a local frame independent of the orientation. So the idea is to include a rotation transformation R in the formulation. So if R is a good rotation at point Qi, expressing the orientation of the local coordinates frame with respect to Pi, then we can apply R to the initial differential coordinate of Pi. So how can we find this ideal rotation? One possibility is to look at the surrounding edges at the point Qi with respect to Pi in computing the vectors Qj minus Qi and Pj minus Pi. And we can compute the covariant matrix sigma of these vectors. This gives the best local transformation between Pi and Qi. Then we can actually extract the best rotation from this matrix using the polar decomposition we already saw. And R is equals to the polar decomposition of sigma. So we can compute this rotation R, but one of the problems now in our formulation is that the expression of R is nonlinear with respect to Qi, which means that the global energy E is not quadratic anymore, so we cannot use directly a least square method to solve it. So one of the ideas to avoid actually nonlinear optimization is to split the rotation part and the Laplacian part in interleaving and iterating between these two steps. So first, we find the optimal rotation R of Qi with fixed Qi, and second, then we find a new Qi position in optimizing the energy E with fixed rotation R. So for fixed rotation R, we have again a quadratic representation, and we can use the least square solver. Finally, using such approach allows to have the surface that rotates automatically, and it can help to better preserve the appearance of the deformed shape. The drawback is that the solution is now slightly more costly, as we need to iterate on several steps and compute iteratively the polar decomposition of each vertex. Fortunately, only few iterations is usually needed to improve the result. And this is an example of the method. We can see that the shape mostly preserves its rigid appearance unless the constraints are forcing it to elongate. And here is a slide on various other approaches to deform smoothly surfaces, as the Laplacian deformation is only one of them. There has been approaches based on gradient, which is another way to represent differential coordinates. Similarly to the cage deformation, the use of bi-Laplacian instead of Laplacian can help to reach even smoother deformation. There is also work trying to explicitly represent the local frame coordinates and make it more naturally rotation invariant. There is also approaches that propagate an initial deformation toward the surface of the mesh. And finally, if you want to know more, there is a state-of-the-art on differential coordinates used for surface deformation from 2008.